Alright, we're back. Sorry. Yeah, so I found the problem, which was that the just simply searching for bin size was not, yielding in anything because apparently there was not enough context for the system on the back end. But when I looked up this whole term, bin size of this one, then it identified what I mean by bin size, right? So let's see here. Uh, okay, it's basically like 2 units above 70. So they're basically using different bin sizes for the histogram. Wow, okay. I should have known this because this is like basic statistics stuff, right? For histogram. Like I somehow got lost in the details. But so basically, yeah, when it comes to above 70, the accuracy is above 70. They percent 70% because this is a percentage score, right? When the accuracy is above 70%, uh, over here they use a bin size of 2 and 2 units, and otherwise they use 5 units. What's the unit? Bin size of 2 units above. I don't know what 2 units mean. What unit is this? Hmm. Okay, I have no idea what this means. Each aggregate point. Maybe I'm just getting too much into the weeds and I'm losing the context. But like each point aggregates a range of a row timer is okay. So the correlation between backbone accuracy and sidechain accuracy. Okay. So fraction of correct row tamers. This is the number of row tamers that were correct, and this was the predicted LDTA. I see. So basically, as the LDTT, LDDT, however you pronounce it, as the LDDT goes up, which means the prediction accuracy of the overall auxiliary carbon atoms goes up, the percentage of correct row tamers of correct side chains also goes up. So basically, the better the model is at predicting the backbone structure, the better it also is at predicting the row tamer, the torsion angle, right? And these buckets, I don't know what 2 units above 70 and what that means, but I'm gonna let that go for now. Points correspond to the mean accuracy. Error bars are 95% or the mean on a per residue basis. 5% constant student T set. Okay, on a per residue basis. Oop! Hit today's goal. Hardcore. Why is it taking so long? Okay, there's a server error. Apparently, apparently Gemini is like. Okay, now it worked. Yeah, sometimes the backend API causes problems, but whatever. The student t-test is a statistical tool used to measure significant difference between the averages of two groups. A large value t-value suggests a significant difference. The bigger the difference, the lower the spread, the more confident we can be. The okay, 95% confidence intervals of the mean on a per residue basis. Alright, fine, whatever. Confidence score compared to the two accuracy on chains. That's number C. Uh, Average PLDD LDDT on the resolved region, and the LDDT carbon axis. Okay, this was the predicted LDDT, and this was the actual LDDT, right? And as it goes up, it was like almost here. All the data points were almost here, and it's you know this is the align that they try to fit on the data. And let's see. Yeah, the confidence score, least square linear fit. Okay, 10,000 protein chains. The shared region, 95% confident. Okay, added quantification of reliability as a confidence score is provided. Okay, basically means that their own prediction of the test score is very good, right? Then finally, D is correlation between PTM on the resolved region. PTM. Let's look at what that is. Predicted template modeling score, confidence measure for the overall structure prediction accuracy. Oh, okay. So the predicted TM and the full chain TM score. Full chain TM score, I believe. Let's see what that is. Full chain TM score helps us compare how similar two proteins are. Okay. Wait to know if our protein TM score is number 1. Clearly downweights big differences because a few bad predictions. Okay, this is the interesting part. Like it downplays big differences because some bad prediction. It's like partial credit. Okay. Okay, it compares how much of the predicted structure overlaps well with the actual structure. The full chain part means that the calculation considers the entire sequence and makes comparison across all the amino acids. Okay, and the PTM. Let's see what this means. Oh, whatever, nothing useful here. Uh, least squares linear fit. Score times PTM. shaded region of the linear fit represents 95% control. Alright, I'm not that in least squares linear fit TM 0.98 times the PTM plus point Pearson's. Okay, I don't know what this is. Pearson's are it's a measure of the linear correlation between two sets of data direction. Pearson correlation coefficient, how strongly two things are related linearly. If one thing goes up, two things go up. Okay, so it's like how to define if correlation, how strong the correlation is basically. Minus 1 and plus 1, okay, 0.85. So a plus 8.85 is a good positive linear relationships, right? Okay, fair enough. So basically, this shows again good correlation, more show offy, right? More show off, like more positive brownie points for AlphaFold and its accuracy. Alright, AlphaFold greatly improves the accuracy of protein structure prediction by accommodating novel neural act and training procedures based on evolutionary, physical, and geometric constraints of protein structures. Fair enough. I remember multiple sequence alignments. Okay, pairwise. Okay, multi-sequence alignments, right? Are okay. Multi-sequence alignment is like lining up multiple lines of strings of letters. And pairwise features, I think we also went through later previously. Pairwise evolutionary correlations. So multi-sequence alignments is like there are two different kinds of features in a way that um, a new output representation and associated loss that enable indirect accuracy. Okay, so these are like techniques to how they made the deep learning model actually work. You know, what kind of data do you feed it, which is these, right? And then how do you represent the output and get the correct, also have an associate loss. This is about deep learning. I'm already familiar with this, but if you're not, yeah, that's basically multiple sequence alignments message, right? Let me actually just look it up, this whole thing together once for this freshness, I guess. Okay, PRS features and multiple sequence alignments. It's a way to arrange three or more biological sequences so that you can see whether they are similar or different. Several sequences share similar regions. They likely came from a common ancestor. Okay, fair enough. And then the pairwise features. Looking at relationships between pairs of things rather than just individual things themselves. Mm, we'll see. Have to see that how it works later, right? Equivariant attention architecture. Let's see what that is. Attention mechanism where the output transforms consistently with input transformations. Okay, equivariance first in deep learning or machine learning, right? I see. So I've already kind of marked it as unfamiliar previously. I've seen this before. Imagine you have a machine that recognizes cats in pictures. Show it picture, okay, it says cat. Now you rotate the picture 90 degrees. Equivalence means that if you rotate the picture before feeding it to the machine, the output will also repeat rotate the same way. Equivariant attention. It's a special kind of attention mechanism used in deep learning, particularly when dealing with data that has some kind of symmetry, like images that can be rotated or translated. Mm. Mm. Basically, an architecture that understands, that is aware of symmetries and awareness of rotation and things like that from the get go. Okay, that puts attention on that. They use intermediate losses to achieve iterative refinement. Okay, intermediate losses. So they train the model like bit by bit instead of the whole model directly necessarily, and masked MSA loss to jointly train with the structure. And learning from unlabeled protein sequences using self-distillation and self-estimates of accuracy. Okay, all of these are techniques tricks that they use to build AlphaFold, right? Which we will learn about in later. Okay, training a model to mimic its own predictions to improve performance on unlabeled data. Making models smaller and faster without sacrificing to. Normally, we train a big complex model. Then traditional knowledge distillation, we train a smaller model to mimic the teacher's predictions. Okay, and self-destination is different. Okay, here the model trains itself. It uses the predictions from earlier stages of training as a teacher. It uses its predictions from earlier stages of training as a teacher signal to guide its later learning. Oh, okay. So, but how does that help you learn from unlabeled? Like self-supervised. Okay, so you have the data already, and you have. Okay, I mean, I guess they use the protein. They label the data by itself, by themselves, to feed it back to the model. And I guess that sometimes works. If the data is good enough. Okay, the most important ideas is provided below. The full network and training procedure we will look at in the supplementary methods. I won't go into that for now. I mean, I won't go into that eventually unless I am really interested. Network comprises two main stages. Okay, the first, the trunk of the network processes the inputs through repeated layers of a novel neural network block that we term evoformer. Produce an end sequence by number of sequences, number of residues that presents and a processed MSA and an okay. It produces two arrays. One is the this array, and then a res by res array that represents residue pairs. Okay, the MSA representation is initialized with the raw MSA. The evoformer blocks contain a number of attention-based and non-attention-based components. Yeah, okay, this is like I'll have to learn about attentions later. Uh, but this is the main point, right? Instead of treating all input elements equally, the network learns to assign different weights or attention scores to different parts of the input. Yeah, this is a separate topic altogether. Okay, this is like non-attention based components and attention based components. That makes sense. This one I'm definitely familiar with, and this one I'm like not yet familiar with in a way. Let's look at that for a bit. So key part of AlphaFold. Okay. Imagine a protein structure is determined by many interacting forces. Okay, the information about evolutionary relationships is from the pairwise mutations, the pairwise features, and the structural constraints are from the MSA, right? The sequence itself, basically. And then it repeatedly refines its understanding of the distances, angles. The intuition that by iteratively refining these relationships, the evoformer can solve the protein puzzle. Concretely structured early in the form blocks and is constantly refined. Oh, okay, okay. New mechanisms to exchange information within the MSA and pair representation that enable. Okay, so basically, this is the key innovation, right? to use both of these different types of data. It's like integrating both types of information you have about proteins to enable reasoning, right? By making many of these data pairs in a way. And then the trunk of the network is followed by the specific 3D structure prediction, right? I think it was here. So the input sequence, which is the genetic database search, right? Yeah. So look here, right? There's the input sequence goes into there's an input data structure sequence, right? That first you search for other proteins which have a similar structure, the sequence, similar sequence, multi-sequence alignment, right? Which sequences are similar to it, and then you find also pairwise features. So pairwise features is basically where you have templates and these homologs which evolve together, right? And based on both types of information, you feed them into a model, right? And you're getting like, okay, pair representation and the MSA representation makes sense, right? You put that into evoformer, which has both attention mechanisms and non-attention mechanisms. You get into a okay, so and then you keep putting back this information. Interestingly, I don't know how that works. There's like a loop within the network 3 times, right? And then you send it to the. So this is a refinement of the understanding. Huh. I guess this is like an encoder decoder structure information, right? You maybe encode this information and then you try to decode this information to make sure the model really understands what's going on, right? That makes sense. And then you feed it back again, feed it back again, and feed it back again. 3 times. This is the core, right? What's going on? And then you have the structural prediction block, which gives the actual positions. Okay, let's go back. Yeah, introduce a 3D structure in the form of a rotation and translation of each residue. Okay, so for each residue you have two values predicted. One is the rotation and one is the translation, that the actual position, right? Initialized in a trivial state with all rotations set to identity and all positions set to origin, but rapidly develop and define a highly protein structure with precise atomic details. Okay. Key innovations in this section of the network include breaking the chain structure to allow for simultaneous local refinement of all parts of the structure. Simultaneous local refinement of all parts of the structure. A novel equivariant transformer to allow the network to implicitly reason about the uh, a novel equivariant transformer to allow the network to implicitly reason with unrepresented side chain atoms and loss term that listens essential weight on the orientation correctness. Okay, these are like hidden tricks in the network. Unrepresented side chain atoms. Okay, unrepresented side chain atoms Imagine a protein like a complex Lego structure. Each Lego is an amino acid, whatever. Da, da, da. When scientists use computers to model proteins, sometimes they don't see all the atoms in those side chains. Hmm. Okay. So it reasons about those missing or underrepresented side chain atoms. We reinforce the notion of iterative refinement by repeatedly applying the final laws to outputs and then feeding the outputs recursively into the same models. Oh, okay, interesting. The final loss, right? Here, the final loss is also added to this recycling and then fed back. Hey, like you're not doing well. Here, you're not doing well, right? Uh, so these are constantly trained, retrained, and retrained all the time. Okay. Marks accuracy with minor extra training time. Okay, fair enough. Okay, and finally we will get to the Evo former. Let's see how long we've been going today. Okay, we've gone 30 minutes, so let's stop here for today. And in the next video, the next live stream, we will go over this Evo former block. Again, I'm the founder of Sandpram Research, the company, and the tool that I've been using is called DenseWiki. Uh, that you're welcome to use here, right? This is the tool, DenseWiki, and you can find it at densewiki.org and play with it. And for now, signing off.